Electricity was not invented by a single person. It was always present in nature, hidden in lightning, inside matter, and even within the human body. What humans had to do was discover its behavior, understand its laws, and eventually learn how to control it. That story stretches across more than 2,000 years. Around 600 BC, the ancient Greek philosopher Thales of Miletus noticed something strange. When amber was rubbed with materials such as fur, it could attract tiny lightweight objects like feathers, dust, or pieces of dried grass. To people at the time, this must have seemed almost magical. There were no wires, batteries, generators, or electrical instruments. They had no idea that rubbing two materials could cause an imbalance of electric charge. Today we call this static electricity. And interestingly, the word electricity itself would eventually be connected to amber. The Greek word for amber is electron. But for nearly 2,000 years, electricity remained little more than a strange curiosity. That began to change in the late 1500s. English scientist William Gilbert carefully investigated magnets and the mysterious attractive force produced by rubbed materials. Gilbert tested substances such as amber, glass, sulfur, and various stones. He discovered that the effect was not unique to amber. Different materials could develop the ability to attract lightweight objects after being rubbed. In 1600, Gilbert published his famous scientific work, De Magnete. He used the Latin term electricus, meaning something like of amber, to describe this strange phenomenon. Electricity was beginning to move away from superstition and toward experimental science. But scientists still had a major problem. They could observe electrical effects, but producing electricity reliably was difficult. Then, in the 17th century, German scientist Otto von Guericke built one of the earliest electrostatic generators. He used a rotating sulfur globe that could be rubbed to generate static electricity. Instead of waiting for the right materials to accidentally become charged, researchers could now deliberately create stronger electrical effects. Scientists across Europe began experimenting. They produced sparks. They attracted and repelled objects. They even noticed that electric charge could sometimes jump through the air. Then came another breakthrough. In the 1720s, English scientist Stephen Gray discovered that electricity could travel from one place to another. During his experiments, Gray found that some materials allowed electric charge to move through them easily, while others did not. This helped establish the distinction we now describe using the terms conductors and insulators. Metals were good conductors. Materials such as glass, silk, and resin could act as insulators. This discovery completely changed the way scientists thought about electricity. Around 1745 and 1746, experimenters in Europe developed a device known as the Leyden jar. It was an early capacitor, capable of storing electrical charge and releasing it suddenly. For the first time, researchers could collect a significant amount of static electricity and discharge it when they wanted. But one enormous question remained. Was the electricity produced in laboratories related to lightning? At the time, lightning was one of nature's most terrifying mysteries. Then Benjamin Franklin entered the story. Franklin studied electrical phenomena and developed important ideas about positive and negative charge. He suspected that lightning was an enormous electrical discharge. In 1752, experiments associated with Franklin's famous kite investigation helped demonstrate the electrical nature of storm clouds. The popular image shows Franklin standing in a thunderstorm with lightning directly striking his kite. That is misleading. A direct lightning strike would have been extremely dangerous and potentially fatal. That breakthrough arrived around 1800. Italian scientist Alessandro Volta had been involved in a scientific disagreement with another Italian researcher, Luigi Galvani. Galvani had noticed that the legs of dead frogs could twitch when connected with metals. He believed this revealed a special kind of animal electricity. Volta suspected something different. He believed the metals themselves were playing a crucial role. To test his idea, Volta experimented with different metals separated by materials soaked in an electrolyte. Eventually, he stacked alternating disks of metals such as zinc and copper, separated by electrolyte-soaked material. The result was the voltaic pile. It was one of the first practical batteries. Unlike static electricity machines, Volta's device could produce a relatively continuous electric current. Then, in 1820, Danish physicist Hans Christian Ørsted noticed something remarkable. During an experiment, an electric current flowing through a wire caused a nearby compass needle to move. Electricity was somehow creating a magnetic effect. This was a major clue. Electricity and magnetism, which had previously seemed like separate forces, were connected. French physicist André-Marie Ampère quickly investigated this relationship in greater detail. His work helped establish the science of electrodynamics. The electrical unit ampere, or amp, was later named after him. But the discovery that would transform electricity into a practical source of mechanical power came from Michael Faraday. Faraday had little formal education, but he became one of the greatest experimental scientists in history. He asked a powerful question. If electricity could produce magnetism, could magnetism produce electricity? In 1831, Faraday found the answer. He discovered electromagnetic induction. When a magnetic field changes around a conductor, an electric current can be induced in that conductor. This principle became the foundation of the electric generator. Instead of depending entirely on chemical batteries, humans could now generate electricity using mechanical motion. Faraday had uncovered the principle that would help make large-scale electricity possible, but generating electricity was only part of the challenge. The next question was how to turn it into something useful for millions of people. During the 19th century, inventors and engineers developed electric motors, telegraph systems, improved generators, and electric lighting. Thomas Edison and his teams worked on practical incandescent lighting systems and electrical distribution. In 1882, Edison's Pearl Street station began supplying direct current electricity to customers in part of New York City. But direct current had limitations for transmitting power efficiently over long distances with the technology of that era. Another electrical system was gaining attention: alternating current, or AC. Inventor and engineer Nikola Tesla developed important AC motors and polyphase electrical systems. Industrialist and inventor George Westinghouse became a major supporter of alternating current power distribution. AC voltage could be efficiently stepped up or down using transformers. High voltage made long-distance transmission much more practical because the same amount of power could be transmitted with lower current, reducing resistive losses in wires. This led to the famous competition between AC and DC power systems during the late 19th century. Eventually, AC became the dominant system for large electrical grids. A dramatic demonstration came with the development of hydroelectric power at Niagara Falls in the 1890s. Large generators converted the energy of moving water into electricity, and AC technology helped transmit that power to consumers farther away. Something that had begun thousands of years earlier with a piece of rubbed amber had become an industrial force capable of powering cities. And the story continued. Scientists eventually discovered that electric current in metals involves the movement of electrons. In 1897, J.J. Thomson provided experimental evidence for the electron as a particle smaller than the atom. Electricity was no longer understood simply as mysterious sparks or invisible fluid. Thales observed static effects. William Gilbert studied them systematically. Stephen Gray showed that charge could travel. Benjamin Franklin helped connect lightning with electricity. Alessandro Volta created a continuous source of current. Ørsted connected electricity with magnetism. Michael Faraday discovered how magnetism could generate electric current. And later, engineers transformed those discoveries into practical electrical systems. Electricity was not discovered in one laboratory on one particular day. It took more than 2,000 years of observations, experiments, arguments, accidents, and breakthroughs to understand a force of nature that had been surrounding humanity all along.